So respected Professor Dr. Anup Kumar Sood is with us. He is a professor of mechanical department in the Institute of um, National Importance. So he is from National Institute of Advanced Manufacturing Technology, Ranchi, formerly known as NIFT. So Professor Sood is the head of the mechanical department of that institute. His main research interest includes additive manufacturing, metallization of plastics, application of soft computing techniques in design and manufacturing, and mathematical modeling of manufacturing processes. His name has been listed consecutively for 3 years in the 2% most cited scientist list prepared by Stanford University. And I personally know Professor Sood is a wonderful person. He is a expert in the field of additive manufacturing. I have seen his work. So he has done some exemplary work in the field of 3D printing. So Professor Sood, in spite of his busy schedule, he has given us his valuable time. So we'll hear from him today. We'll learn from him. We have the opportunity to interact with Professor Sood. Sir, the stage is yours.
Thank you, sir. Thank you, Professor Gautam Bose. Thank you for first of all inviting me to this faculty development program. Now, my lecture on this FDP is, let me first start my slide. So I believe that I'm clear to everyone. My voice
Loud
is
and clear, sir.
and you are able to see my slide there.
Absolutely.
Now, my topic of presentation is understanding additive manufacturing for micro fabrication. Now, I have knowingly choose this topic. Okay, why instead of going for the direct application and some examples and research what is happening in micro fabrication related with additive manufacturing, I think it is essential for us to first of all develop our understanding on this process. The reason being that why I think like that understanding is needed. Like first additive manufacturing machine comes into picture in 1985. And first micro additive manufacturing machine, that is micro stereolithography, came into picture in 1993. And after that, there is no much development in this area. Most of the micro additive manufacturing is in research area or lab areas. There are very few commercial micro additive manufacturing machines are available in market. Now, to understand the reason why it is like that, it is important to us that what is the constraint that micro fabrication is offering to additive manufacturing. And for that, we need a proper understanding of this thing, that what is actually the additive manufacturing and how we can change this or make it more suitable for micro fabrication purpose. If I give you a very simple example, like in additive manufacturing, we require to represent any object in an STL format, which is nothing but a triangular representation we use. So we are basically representing any surface with a triangle there. Now, when I have to discuss about the triangle is represented using its 3 vertices there. Now, at the micro scale level, where my component is in micro level and this component is having the features which are at a sub-micron levels there, I am representing those things with a triangle which is having a vertices, 3 vertices. Now, these 3 vertices need to be spatially distinguished there. Now, at that level or that micro level, these vertices may have some precision value which my software may able to read it accurately to distinguish them spatially different there. Okay, and at that scale, it may not be possible to read. It may happen that all these 3 vertices may collapse into one, and we instead of getting a triangle, we get a point. So, is it a right approach to represent a CAD model in a triangular representation for the case of microfabrication? Or if I take another example, like in additive manufacturing, we convert our feedstock into a solid three-dimensional representation using some energy source. Now that energy source is having its own heat affected zone. So that heat affected zone may affect the dimension or roughness requirement at the micro level. So we need to think some alternative ways to use this additive manufacturing. This layer by layer addition process has proven its potential in the case of macro manufacturing. And it has shown that it is easy to go for a fabrication in a layer wise layer manner. So to adopt this thing for the case of the micro scale level, we have to go for a layer wise layer, but what changes or what how much how can we tweak or major changes or maybe a minor changes can be done in the process itself to make it more feasible for the micro fabrication, and we can move from the research level to the commercial availability of these machines there. Now, to understand that thing, we need a basic understanding of additive manufacturing. With that point in view, I've presented my this lecture, and I hope I may be able to develop some interest in this area for researchers to take this opportunity to improve additive manufacturing for micro fabrication. Now, what is actually aim for micro manufacturing when we talk about? When we talk about this word micro manufacturing, it has often two meanings. First is manufacturing of small number of parts using minimum manufacturing facilities. Or another meaning can be a manufacturing of parts at a small size. Now, if you look at the additive manufacturing, it can fit into both the definitions. With the additive manufacturing process, we can manufacture a part in a very small batch size, maybe consider one or few, by using a minimum facilities there. Just only additive manufacturing machine is enough, and after that some post-processing requirements are need to be fulfilled to get the final part suitable for practical applications. So and for the second definition, that using this for making a part at a micron level there, and that part may have the features which is in the sub-micron levels, we can again adopt this technology to getting the micro level parts, or for the case of the micro manufacturing. Now, there are some of the examples I am showing you which have been built with the help of micro scale additive manufacturing. As you can see, we can use these additive manufacturing process to generate a complicated artifacts at a very small scale. You can appreciate the scale by considering the presence of some macro level features, like you can see the keyboard keys here, above which these artifacts has been placed. You can understand the level of scale I am talking about there, and you can able to generate these type of complicated microstructure. You can have micro scale production for practical applications like medical application, and even in a case of macro size part, you can have a micro size features. So additive manufacturing can be adopted for micro part production as well as generating a micro features in any part depending on the requirement. Now, question is why we require micro additive manufacturing. We understand there are a lot of micro manufacturing methodologies or processes are already available there. So why we are interested towards the micro additive manufacturing, or why we are interested towards the additive manufacturing application in the micro scale production of the component. Now, most of the available micro fabrication technologies which are there, they may be able to generate a complex microstructure, but that is in the 2.5 dimensional space there. But they have some restrictions. Like if I want to generate a part using a diverse material, like at certain location I want one type of polymer and another location different type of polymer, The existing microfabrication technology may not be suitable at that scale. We may not able to generate high aspect ratio part using these existing methods there, like the parts, like if I have to go for a profile cutter, say a small drill with some dia and some big length there, the existing process may not be suitable for that case. We may adopt additive manufacturing to get such type of high aspect ratios components there. Biggest advantage is additive manufacturing is giving us that we may able to have a functional integrated parts there, right? Instead of producing different parts in a sub component, I can generate a consolidated part as a single unit. All the component consolidated together as a single unit can be produced there, and these single units can be have a functional performance asset. They may have a motion or some type of other functional requirement. That is the advantage these additive manufacturing machines are able to provide to us. So we can say that we can consider this additive manufacturing as one of the capability to enhance the microfabrication area there. So it is not that we are replacing all the micro manufacturing technology with the additive manufacturing. It is not like that. It is that this is one of the addition, and this is one of the useful and important addition in this particular area. Now, this micro additive manufacturing has great applications here. We can use these micro components for miniature motors and turbines, micro satellites, implantable medical devices, minimally invasive surgery equipments, micro robots, miniature molds, and dies there. So a lot of applications can be think about of these parts there. Now, before going further, let us first understand that what actually the additive manufacturing means there. Earlier, this technology is known by the name of rapid prototyping. Now, after that, and some of the researcher or user may have also used acronyms like designating the particular technology like selective laser melting, laser engineering net shaping, or direct laser melting. Sometimes type of acronyms are also used to define these technologies there, and some people used to call it as free-form fabrication, layer by layer manufacturing. Well, so many names were there. Later on, ASTM established a standard, and they defined a standard name that is known as the additive manufacturing. Still, till this date, this technology is also named by another name that is known as the 3D printing. But as per the ASTM standard, the standard name is additive manufacturing. Now, what is actually additive manufacturing is? Now, if I consider a simple example, like if I have to say apply henna over my hand, so what I will do, I will use a cone which contain that henna or mehendi, and by applying the pressure, that henna will come out from the tip of that cone and it will spread over my hand. Now, if I look at, I can move my hand as per the design requirement, and I will get the required profile over my hand or required design over my hand of that henna. Now, if you look at that henna which I have mehendi I have deposited over my hand, it profile is a 2D. I can generate a complicated 2D profile here, but in the third dimension, that is the vertical dimension I am talking about, that profile is basically having no features there or no element present. It is a simple profile there. So this way I have generated one layer. Now above this layer, if I deposit another profile matching that layer constraint there, in this way I will able to grow entire 3D part. The additive manufacturing also based on the same principle. In this principle, we have the robotic arm which will move. That robotic arm may be carrying a extruding material or maybe a power source, and it will move as per the layer profile requirement, and it will generate a layer profile, and this profile is generated over a table, and when this table will move downward, the next layer will be generated over that. In this manner, we are able to consolidate these layers one above each other and able to get a 3D structure. Now this, as you can understand, this is a very simple way to generate a complicated structure. Like if I consider a complicated structure, it is easy for me to represent in orthographic views there, like front view, side view, top views there. Okay, but if someone asks me to draw them in a 3D, it may be difficult for me there. The same thing is here, that I can able to generate these complicated structure in a layer wise layer manner, and these layers are known as 2.5D layers there. Okay, so this is about the additive manufacturing. Now, under this additive manufacturing, there are a large number of machines are available, and all these machines are basically been classified into 7 categories depending upon their part build methodology there. So these categories, as defined by the ASTM, are material extrusion, powder bed fusion, wet photopolymerization, material jetting, binder jetting, sheet lamination, direct energy deposition. Each of these method has limitation of use of material, and it has own build principle. Like material extrusion, simple example is a fuse deposition molding machine, FDM machine, or current days it is fuse filament fabrication, triple F. Okay, so that is example of the material extrusion machine here. Okay. So there are various categories of those things there. Now these process have their own advantages there. First of all, we are able to get a complicated part here through these process, because as I explained to you that it is simpler for us to uh, grow or generate a part in a 2D manner by layer manner, by depositing one layer over another layer, and in this way can able to generate a various complex geometries there, especially those geometries which are generated using a mathematical algorithm like topological or a shape optimization algorithm. The type of geometries they generate, they are quite complicated than the simple structure with the conventional manufacturing process can generate, because they are been generated based on the functional or the structural strength requirement there. Additive manufacturing can generate a part based on the functional or the structural strength requirement, and this processes does not require alternative processes, like you have to go for a heat treatment, you have to go for a first casting, forging, heat treatment, machining, finishing. These type of different processes are not required. There are only very few simple process changes there. So we can say comparison to other manufacturing process of making a component, these process are having better speed there, or they can then build a part with a better speed and accuracy there. We can customize the parts with the help of additive manufacturing as per the customer specific requirement. Yeah. This has bigger application in medical areas there, where we can generate the implants as per the customer specific requirements there. And whatever the part we can generate, since we can generate topological optimized part there, so we can have an internal structure which is taking a less material there. So we can have a lightweight designs using these parts there, this process there. Another advantage this process involved as compared to the conventional manufacturing, that it is a tool-less process. We don't require a particular mold or cutting tool or a die to fabricate any geometry, either simple or a complex. Okay, same machine can able to fabricate a different type of geometries, different type of shapes there. So we can so this is the advantage which is result in the reduction in the cost of the component there. Then this is in sustainable environment friendly process there. We are able to use the maximum amount of material that has been feed to generate a particle. So the wastage of material is very less there. And these parts can be print as per demand. So suppose if we are using some machine and some component is broken, there is no need to um, um, buy it from your OEM. You can build it in your shop floor itself using these machines there, as when required there. So there is no need to keep them those components in inventory or some storage there. So that is the advantage these processes are offering. And obviously, since this process has put more stress on the design aspect, that the design should be as per the functional requirement. So this is giving us the more and more opportunities for people specialized in the area of design to be able to get employment in this area. Now, despite there are so many advantages, but there are basically two advantages which are attractive for the case of the micro manufacturing. First one is that the AIM allows the manufacture of components without many of the geometric limitations that constrain subtractive and formative processes. Since I am generating any 3D part in a 2D manner, a layer by layer manner, I am generating. So this layer specification is simple. Like if I have to want to generate my body structure, so there I can divide my body into simple layers there, and I can place one layer above each to get my body structure. Or if I consider a simple example of a cylinder, say if I am stacking one coin over another coin, and I will get a cylinder. So whatever the geometric limitations that can be overcome, and these processes are able to generate all type of complicated parts there. In other manufacturing process, you require a mold, then you require a die, or even you require a cutting tool. When you are using cutting tool, you have the accessibility problem, but that may not be true for this type of process. So this is the advantage which has attractive researchers towards the application of this process in a micro fabrication. There is another advantage of this process is that AM enables the production of small quantities of potentially customized products at a comparatively low average unit cost. Now, AM actually, additive manufacturing actually build component in a controlled environment there. Okay, so as a result, this produce constraint on the size and the number of the component that can be produced. This may be disadvantage in the case of the macro, but this is advantage in the case of the micro manufacturing. So these are the two important advantages which has attracted many people toward this additive manufacturing process application in the micro fabrication. Despite so many advantages, this process has own limitations like limited selection of materials and characteristics. We cannot use every type of material. There is certain requirement that need to be fulfilled by that material. A good weldability property, we should able to convert into powder, or a type of feedstock we required there. Obviously, this process has low process productivity. We are not able to use this machine for a mass production there. We can produce a batch of one or two or similar few items using this process there. This process still suffer with a low accuracy of product dimensions. Later on in this presentation, you will understand what are the limitations, why it is like that there. It has a poor surface finish. Process is not reliable. And that means if I am producing a component, if I'm using the same machine, and if I produce the next component, similar component next time, I may not get the similar properties there. There may be large variation there. Okay. So these may are certain of the advantages, but the basic process chain, if we understand, for additive manufacturing, we require a source of a geometry. It can be an object, or it can be a designer itself. A designer can create a model, which we call it as a 3D CAD model, or it can be in some object, already existing object. There we can use a reverse engineering techniques to generate the data from the object, which we call as the imaging system, to get a required CAD model here. And then we have to manipulate this geometric data as per the requirement of the additive manufacturing process there. And then this data is fed to the additive manufacturing machine for building a three-dimensional physical component. Now, if we talk about the basic process chain of this additive manufacturing process, it starts with the development of CAD model. which is to be converted into a suitable data representation format. De facto standard is a STL representation, and this then is being sliced into different layers, because we have to, these layers are to be deposited one over each other. So we have to slice this STL represent or this CAD representation into layers there, and this machine will produce one layer above the another layer, and for that, for first layer, for each layer, this machine will first generate an outer contour, and once outer contour is generated, then it will, since the inner portion is also solid, so it will do the inner filling of the region between the outer contours there. And after that, one layer is generated, the next layer will be deposited over it, and in this way we will get a 3D part there. Now our aim is to understand this process chain and see that how it can be made more suitable for the micro fabrication here. So we need to understand that why these elements, or why these elements of this process chains are important for the case of additive manufacturing. And later on, as a researcher, we can think about that how we can what changes we can induce to make them suitable for the micro fabrication. The first of the requirement in the additive manufacturing is the transfer of a data. We have seen that for additive manufacturing we require basically a CAD model, which is a three-dimensional CAD model, which is actually a solid or a surface representation of a object. The source of this CAD model, as I have already told you, may be already existing object which has been scanned through reverse engineering technique, or maybe a designer itself who will create that CAD model. Now, when this CAD model is required, generally design and manufacturing take place at different locations there. We need a transfer of this mathematical description of an object to a manufacturing unit. And for that purpose, we require a data transfer format here. That is true for all the manufacturing process. Okay. And to make this data transfer fast, we may go for an electronically transfer. But this aspect is true for all the manufacturing processes we know. Now, but if you look at the basic process planning state, which we have discussed in a previous slide, what we do with this data. So we use this data, that is the CAD data or the mathematical representation of an object, to first decide the orientation of an object. Later on, you will understand why the orientation object is needed there. For deciding the object orientation, we require the information of the 3D shape of an object. Then there are many additive manufacturing machines which require a support structure. You cannot build overhanging structure without a support in many of the additive manufacturing machines like fuse deposition modeling or stereolithography. But there are some where you may not require that much extent there. So for support structure design, again, from which feature required a support structure and from where the support has to be provided, we require a information of a model there. So that means again we require a CAD information or a mathematical description of that object there. Then next stage is the slicing. We need to convert this CAD model into 2D slices there. For the slicing purpose, slicing is required because the machine will generate the profile of each slice over another to get a 3D part. For slicing, again, we require a CAD description there. Then, as I have shown you that in each slice, first the outer contour is deposited and then the inner portion is solidified or inner portion is covered there. So that is come under the path planning for each slice. That can be again done using that mathematical description. And we need to optimally utilize the build volume or the build space there. So we can place multiple parts together to be built simultaneously using an additive manufacturing process there. So for that, again, we required that how to cover the volume optimally. we require this information. So in this process planning steps there, the important information which are required is the description of the shape of an object, the material data, that is the material from which this object is to be built, tolerance information, process parameter setting, and surface finish operations. These are requiring that. First, we consider the geometric related process planning input. Okay, so we require a model. Now, this model representation can be a surface model or a solid model. Okay, or even if we are using already existing model and using imaging system, we may get a point cloud data. A surface model or a solid model is nothing but the mathematical representation of an object, so that our CAD software may able to generate that representation. Because simply, like, if I have to make any CAD model, I need a program. For making a program, I need an algorithm. Now, how to build that algorithm? So algorithm need to be built on some logic there. So we go for a mathematical description of an object. We manipulate these mathematical descriptions. Like if I have to make a line, I require a mathematical definition of a line. Computer will not able to get a line simply but just by saying that I want a line. I need a program which is based on the mathematical description of a line. So that mathematical description can be specified as a surface model or a solid model. There is a third type, that is a wireframe model, but that is not being used here. Okay. So when we talk about the surface model, it is a surface representation of an object. That means we assume that we consider in surface model that we envelope entire object with the help of a surface, and since the object may be three dimensional, a single surface may not be suitable to cover that entire surface. So we use surface in a surface patches there. Okay, so these surface patches are to be blended together. Now this blending is done based on some continuity requirement from one surface to another surface there, and this surface edge profile may be such that the continuity requirement may not be fulfilled at all the points on the surface edges. So that means the edges may not join properly, and as a result there may be some puncture or a minute hole may be present. Or in other words, we may say that we may not get the airtight or a watertight model if we use this surface model representation. Airtight or watertight model means that if I assume that I am filling this surface model, that is the mathematical description of an object which I am representing with the help of surfaces there, with some air or a water, because of the presence of this minute hole, which we call as puncture, there will be a leakage there, and I will not get a single volume. That means I will not get a single unit there. There will be some gaps into there. And if I build this object with the help of additive manufacturing, so for additive manufacturing, I need for each layer, I need a close profile. Okay, and because of this gap at a particular location, I may not get a close profile at a particular layer. Okay, because I need to first define the boundary contour. Okay, so I may not get this close profile at a particular layer, so I may not be able to fabricate the part. Then other representation is the solid model representation. The solid models are the complete representation of an object there. It represents the geometrical as well as the topological information of an object, whereas the surface model only represents the geometrical information. Geometrical information means like you may get the dimensional information from the object, but you will not get the connectivity information. Like if the two lines are sharing the same vertex, okay, that is a topological information that is not present in the surface models there. Okay, whether a point is inside the object or outside the object, that is a topological information that is not present in the case of surface model. It is present in the case of solid models. Okay. So we can use surface model as well as solid models in additive manufacturing process, but the best representation is the solid models. Okay, because I already explained to you, in surface model we may have have small puncture or a hole there. Okay, so if you have the choice, then we always go for a solid models there. And there is another representation, that is the point data. If we have already existing geometry, we can, instead of making it from the scratch in our CAD software, we can scan that thing using any scanning method, which are basically divided to two categories. One is the contact type, another is a non-contact type. The coordinate measuring machine is an example of a contact type scanning, and your laser scanner is an example of a non-contact type scanning. So this scanning method will generate a point information on the surface of an object there, and these point informations are arranged. There are some pre-processing steps are involved into a 3D representation, which we call it as a point cloud data there. Now this point cloud data is not suitable for a direct application in additive manufacturing there. Some of the researchers have tried to use this thing, directly a point cloud data, to get a slice information, but the accuracy is very poor in those cases. So it is always advisable to convert this point cloud data into a surface models. So we fit the surface over this point cloud data, and then we can use this surface representation. So it is clear that we require a surface or the solid models or a CAD representation of an object. Once that representation is there, now we have to convert that representation of a CAD or mathematical description of an object into a suitable representation which the additive manufacturing machine can understand. Now there are different varieties of machines available, so we require for each machine a suitable standard, so that I can convert my CAD information into a single data there, single standard representation. So de facto standard is an STL. That means it has, why we call it as de facto, it is not universally acceptable or a good standard, but still we are using it, so it automatically becomes a standard. Okay. Now in STL file, what we do, we actually represent the boundary of an object using triangles there, and this we call as a tessellated representation of an object. Okay, in tessellated representation, we have the triangular representation on object, and each in STL file can be a binary or a ASCII file. Binary file will obviously have the less size compared to ASCII file. Both the files stores the three vertices of each triangle as well as the outer normal of each triangle there. These three vertices are stored in an anti-clockwise direction and outward normal. Outward normal means that the normal to a triangle face is pointing towards the direction which is away from the material side. Material side is, that is the side which is inside the boundary of that surface. Okay, that is the solid side. So outward normal is pointing away from that. Okay, so we have the ordered pair of vertices in this case and an outer normal. That this figure, you are seeing the example of one of the triangular facet in an STL file there. Okay, you yourself can do this thing. You can make any CAD model using any CAD software, and then save as option, you save it as an STL file, and once you save it as an STL file to a save as option, after that you can open that file in a notepad. You will get the STL representation there, and there you will see this type of format represented for each facet there. So basically it represents the facet normal. So facet normal, I say X, Y, Z directions are there, and X, N, Y, and Z values, and then vertices are stored in an anti-clockwise manner there. This is for the case of a single facet representation. Okay. Now the entire object can be divided, as you can see here, into various triangular representations there as per the requirement here. This triangular representation has some of the conditions which need to be fulfilled there. First is that each vertex must be shared by at least one triangle. Then at the sharing cannot be done at the edges. The sharing of the vertex has to be done at the endpoint, that means at the vertex itself. Triangles cannot intersect uh, themselves there. So these requirements need to be fulfilled. Now, why we actually use STL format for my data representation in this case? First of all, it is easy conversion. Almost all the CAD software at present we use, they have this type of representation. Okay, and we can easily convert them. It is very simple. In a file, save as option will be there. So you can save that. In a save as option, you can choose the file type as an STL, and you save your file in whatever location you want to save it, and it will be automatically converted into an STL format. So that is an easy conversion. You don't require a special algorithm or programs to do the conversion process. Okay, and almost most every type of 3D representation can be converted into STL format, and most of the commercially available softwares, they are having this thing to be converted into STL format here. But why we are actually using this triangular representation? Okay, why not any another representation? Triangular representation is nothing but a planar representation. There are many planar objects which we can use to represent an 3D surface there, like a rectangle or any other. But why we are going for a triangular representation? The first reason is that it has the simple slicing algorithm. Now, if I have to do the slicing, why I have to do the slicing? Because I have to convert into this 3D structure into layers. For each layer, I have to do the slicing. Now, for the slicing there, I will use a slicing plane. Now, this slicing plane is intersecting the various edges of the triangle. So wherever these slicing planes are intersecting these edges, like this slicing plane is intersecting this edge of the triangle here. So these points are located in a plane here, as you can see in this below bottom figure here. Okay, like S0, S1, like this. So this slicing plane has cut this particular triangle. Now you can join these points in this plane by a smooth curve, and you will get the layer profile. So this is very simple. We have the simple slicing algorithm. Even if you are interested, you can write a program to get this contour profile here. Another advantage is, as you can see, this slicing is easy. We can able to split our model into multiple pieces. Our object size may be such that we may not able to fit that into a build environment or inside the build chamber there. Okay, it may be oversized there. So what I can do, I can use this slicing ability to split my model into various parts, and I can place these various parts or build these various parts simultaneously in a machine, and later on then I can assemble them. Okay, so that is also advantages. So these are some of the advantages of the STL file. But this STL file has some of the associated disadvantages with it. Like, first is those caused by the triangulated boundary representation. I am representing a 3D surface or a 3D object with the help of a planar triangle. Okay. Now this triangle itself a plane. I am using this planar triangle to represent a 3D surface. This is itself a problem because my 3D profile is maybe having curves here. Okay. So triangle may not be a suitable representation. This is one of the problem. I can overcome this problem by decreasing the size of the triangle. Now, if I decrease the size of a triangle, the number of triangles will increase. In that case, my file size will increase. Okay, and if the file size increase, then it may create a handling problem. My slicing will take time. File size will transfer will take time, so it may create a handling problem. Okay. So we can say that it's representing any 3D surface using triangular representation itself a problematic thing there. Then another problem is those related with the format itself. Now in STL format, STL file, we store this information into a triangular representation. Okay. Now we store many redundant information. Like one of the redundant information, if I am storing a vertex of a triangle in an anti-clockwise direction, so if I am having the vertex information, I can have the information of the edges of the triangle, and using the edges of the triangle, I can determine the vertex normal to the triangle by using a cross product. So why I am then storing a normal? So this is something redundant I am storing. Okay. Then another redundant information I am storing, that each vertex may be stored multiple times. Like if you look at this figure, this particular vertex is shared by other three triangles. But for each representation, I am storing this vertex 3 times. Okay. So this is a redundant information. Then there is another problem, that is a truncation error. This is important for the case of when we go for a micro level manufacturing there. Okay. This vertex, as you can see, has certain precision value. I can store them up to certain precision value that depend upon my system. Yeah. Whether I am using 32-bit or 64-bit system or like that. It may be having certain precision value there. After that, I cannot store there. Okay. So for that, it may do the round off. Okay. And if the round off has been done, then in that case, vertex may collapse into two different vertex may collapse into a single unit there. Okay. So that error may arise there. Another thing is that we don't have, as I told you, we don't have the connectivity information. Like it is not known that this vertex is common to all the remaining triangles there. So this is the topological data is missing there. So this is actually an incomplete representation there. Now, if I am joining two different STL files together to build a single model, and those two STL files have been generated from two different sources there, I may have the tolerance problem there. That what is the minimum size triangle size used in one file or is another file, that may have the inconsistency problem there. Then we may have the inconsistent normal, that normal may not be pointing towards the material, away from the material side, but it is pointing towards the material side. That is known as the inconsistent normal problem. So that's why we store the vertex in an anti-clockwise direction, and through that we check whether the normal is pointing towards the right direction or not. So vertex is stored in anti-clockwise direction, so we can find out the cross product of the edges which are using joining these vertex there. So cross product of edges will give you the direction, and we can check the direction of the cross product of the edges with the normal direction. If the normal is pointing towards the wrong direction, we have to flip it towards the right direction. The right direction is always away from the material. Okay. Then we may have the incorrect normal. In a single representation, the various normals may be in different directions. Maybe. Okay. And this is maybe because of the conversion error, algorithm error there. The algorithm just converted this CAD model into an STL representation. Then we may have the gaps like suppose in high curvature regions there. So I am having this triangle. Now these triangles are satisfying the requirement that this particular triangle is shown shaded here is being shared by other triangle there. So each vertex is being shared there, but still the curvature is so high, and here is an edge here which is a straight line. So I'm not able to represent this curvature. I can overcome by filling another triangle, but then the size will be less there. So it may create a gap. Okay. And gaps may not be suitable, as what I was explaining for the case of the surface model. Also the same problem will arise for the case of the gaps here. Like in surface model, if the puncture is present, so I will not get the closed boundary. Similarly, if the gap is present, I am not getting the closed boundary there. So if I am doing the inner filling, I will not get the end. Okay, suppose my laser is moving to solidify this inner portion, so it has to end. It will continue like this there. So I will get a defective part there, or my build may stop. So these problems are there. Then we may get the problem of degenerate facets there. Like vertex may collapse into a single unit, or triangle may become a line there. So we will get this type of problems there. There are other alternatives also available there, like initial graphic exchange specification, HP graphics language, shape transfer exchange protocol, common layer interface, rapid prototyping interface, layer exchange format, or SLC formats there. Out of these, the first three are already existing, and later CLI, RPI, Leaf, and SLC were specially developed for the additive manufacturing process there. Okay. So each of these has some advantage, some associated disadvantage with that there. But these are some of the alternatives available. Okay. So to this, we need to get an idea that we require a proper alternative to represent a CAD model. At present, the STL is a de facto standard there. But whether for the micro scale fabrication, we can still use STL or not, that is not clear. Next step is when we build a part in additive manufacturing process is to decide the orientation. Like if I consider cylinder here, you can see that there are two different orientations the part is built. So the part, what is the meaning of orientation? The part is built in a layer-wise layer manner. So I am depositing these layer one over each other. Okay, so uh, this is a layer profile, and the part is being grown in this direction. Layers are being deposited along the Z direction. So this is my build direction. So I can specify the orientation of my part with respect to this build direction. So if I am building part like this here, so I can see that I'm getting a smooth surface. But if I've oriented the same part like this, and I'm depositing my layer again along the Z direction. Okay, so I will get a profile like this there. We call this thing as a staircase error. As you can see here, hemisphere here. So this curved portion is here. So I'm using this rectangular profile to represent my layer. Because they are not able to represent it completely. So I'm getting a stair type effect. We call it as a staircase error. Okay. Now, for simple geometries, I can eliminate this staircase error like for the case of cylinder by selecting proper orientation, but then there are many geometries where this staircase error cannot be eliminated. Okay, in that case, uh, we need to decide the proper. There is some disturbances there.
Kosik Mondal, switch off your sound. Kosik Mondal.
Okay, so we can build a part there. Suppose, say I am showing the two orientation of this particular part here. In this orientation, if I build, you are seeing that there are many areas where we can get the staircase error. But if I build the part in this particular orientation, I have minimized the staircase error. So we need to decide a proper orientation for minimizing this staircase error. Now I can minimize this staircase error by refining the layers, by decreasing the layer thickness. So as you can see, if I decrease the layer thickness, I am getting the more smoother surface. Okay. But in that case, then it will increasing the number of layers, and the number of layers is increase, and depositing these layers over one over each other may generate many defects or errors there. Okay. As you understand, this is additive manufacturing is nothing but heating cooling cycles are involved. Okay. So if I am having the more number of layers, the more number of heating cooling cycles will be there, and as a result, the chance of errors like porosity or other type of defects like warpage and shrinkage may be high. But the staircase error will be minimized there. And the build time will also increase if I increase the number of layers. And because of presence of this staircase error, the slices may be completely inside or completely outside of the object here. Okay, like in this case, the manner I am slicing, all the slices are either outside or inside. Okay. But if I'm not choosing a slicing procedure properly, I may get an object where the part of the slices are outside and part of the slices are inside. This will create problem during the post-processing. If I know that I'm going to get an undersized object, I can eliminate that thing in a post-processing phase. Or if I'm going to know that I'm going to get an oversized object there because of the stair steps only, I can use some process to eliminate this stair step. But if the slicing is like this, then partially it is undersized, partially it is oversized, then this is very difficult to control. For that purpose, the slicing procedures are important here. So I can do slicing with the uniform thickness or through adaptive thickness. Uniform thickness means that the entire part can be sliced using the same thickness value, or adaptive slicing means that as per the criticality of the surface, I can choose the thickness, layer thickness value. And under each category, various type of slicing algorithms or processes are available, and I'm not going to discuss them in detail. I can do the slicing of the tested CAD model, that is the STL file, or I can do the slicing of the directly the CAD models. Okay. And for both the cases, different slicing algorithms are available. Okay. So we need to select these algorithms properly. But basically, the slicing approach we adopt are basic in three types: either top-down, bottom-up, or a unilateral slicing. In top-down slicing, what we do that suppose I have sliced using this plane. Okay, so in top-down slicing, the plane, the point where this plane is cutting this profile, that means this point. From this point, I will drop a slice thickness. Okay, so this is top-down slicing. That is this plane. If I consider, okay, this is cutting this profile here. From here, I will drop a perpendicular. This will define the slice thickness. Bottom up slicing, I will do the reverse. Okay, in bottom up slicing, this plane is cutting here. This is the location where this plane is cutting this profile. From this location, I will make a slice thickness upward. Okay, so this is bottom up slicing. Now, in a part, the part geometries are not simple like this. So we need to decide either to make an oversized part or an undersized part. Say that we are providing a positive tolerance or we are providing a negative tolerance there. We have to choose whether at what location we have to go for a bottom up slicing and what location we have to go for a top down slicing. That we determine using this unilateral tolerance slicing, which calculates the dot product between the normal direction of a triangular facet and the part build direction. Okay, so from it is clear to you why actually we require the normal to the triangular facet. So suppose that this is a triangular facet whose normal is this. Okay, and this is the part build direction. Okay, so we require a dot product of these two directions, which we have to calculate, and layers are added based on the sign of this dot product. So if it is greater than 0, use bottom up slicing for positive tolerance and top down slicing for negative tolerance. So if at particular location, if you require to make an oversize and dot product at that location is greater than 0, okay, you have to go for you can go for positive slicing, otherwise for a negative slicing, like that. Then the parts, when it has been sliced, there are many, we cannot build these parts, which we call as overhang parts, without the need of supports there. Like there are many processes like powder bed fusion, which we say don't require support, but actually they also require support. We need to build a support in them also. That depends upon the weight of the part, because below that part there is a powder. If the powder is not able to sustain the weight of the part, we need to build a support to support that overhanging portion there. And support structure themselves act as a heat sink, so they may able to dissipate the heat faster. Okay, so they are required there. A support requirement depend on the part orientation, like this for the same part, 3 orientations are seen. We are seeing for this particular orientation we require a large support structure, here less, and here no support required. So using support is actually a waste material, it is adding to the cost. We need to decide orientation also on a support structure requirement. Now, support structure requirement is based on the critical features, like where we require the more smoothness. If you are using a supports there, the support is going to affect the smoothness of that feature and will deteriorate the roughness, so we will not go for that thing. And we need a part orientation also have to decide based on the critical features, because you don't understand simple thing that state case effect will be there, state step effect will be there. You want to minimize, so you require to decide a orientation based on that critical feature there. You may not, you may want to fit a part in a build envelope, like there are many parts we are building a build envelope there. You want to use this space optimally there. So for that purpose, again, you will go for a workspace optimization. You need a optimum orientation of each part to be built there. So at this is the first step of my presentation, where I have given you the basic about the pre-processing steps involved in the additive manufacturing. And from there, we will move towards the application on the micro additive manufacturing. So if any questions, or if you like to have a short break, we may have it at this point. Or if you permit, I may continue.
Sir, if you want to continue, then you can continue. Otherwise, we can take
Okay.
short break of 5
If
minutes.
someone has some question, they may ask me in this point what I have presented. Otherwise, okay, then I am continuing. Okay, sir. Thank you. So aim of this first part is to understand that how actually the additive manufacturing process works. What are the pre-steps required, which we call as the pre-processing steps, which are required in an additive manufacturing to build a 3D physical part there. Okay, for the macro scale, they are important, but whether micro level, still they are important, but we need to go for some alternative for them. And as a researcher, we need to think about that how we are going to do that. But in next part, we will discuss some of the applications of this additive manufacturing at the micro level, and I will discuss predominantly two particular process. One is the stereolithography, another one is the powder bed fusion process. Now, why I have chosen these two processes there? Stereolithography is, this process is commercially available to build micro size parts there. Okay. Whereas when you talk about the powder bed fusion process, powder bed fusion is very successful in macro scale ranges there. And it is widely used to build metal and alloy parts, polymer parts, especially metal and alloy additive manufacturing, predominantly dominated by the powder bed fusion and the direct energy deposition categories of the additive manufacturing. Despite so much application and the use of the powder bed fusion process, this process is not able to build a part which is less than the 500 micron size there, whereas stereolithography is able to do that. Okay, so that's why I have chosen two distinct things to understand the problems there, to expose the problems of the process there. So as later on, faculty members, researchers can adopt this thing to modify that thing. But it is not like that you only go for the development of new machine. Even the pre-processing stage, which we have discussed till this point, that need an improvement. You have to think after this introduction that how we can improve to be feasible for microfabrication. Now we start with the micro stereolithography process there. Stereolithography process was introduced in I think in 1984-85 by Carl Chuck something like, I'm forgetting the name. Is a 3D printing machine. 3D printing, first 3D printing stereolithography machine has been developed here. And this micro stereolithography was introduced 2 years after that, in 1993, by the researchers at this Japanese institute, Kyosu Institute of Technology, by these two researchers, Ikuta and Hiro. After that, this machine has moved out from the research level, and the commercial machines are also available. And so, just like a common conventional stereolithography process, micro stereolithography uses light-induced photopolymers of liquid resin to create small-size 3D components. But the only difference is that it uses some micron resolution for the XYZ translation stages. For that purpose, the laser spot size of the laser dia is smaller as compared to the classical stereolithography, and this photopolymerization occur in a very small area, and we are able to get a part of size range 1 to 10 micrometer layer thickness. This microstereolithography can be classified as a scanning microstereolithography machine, projection microstereolithography machine, or a sub-micrometric microstereolithography machine. Now, before going into this thing, let us understand what actually the stereolithography is. So, in this stereolithography, we have a vat. We fill this chamber with a photosensitive polymer, and over this photosensitive polymer, we focused an energy source, which is nothing but a laser beam. And wherever this energy source is focused, that region is gaining a heat, and because of the photopolymerization reaction, that liquid is converted into a solid part. Okay, and the laser will be moved as per the profile. Galvanometers are attached, and that will reflect that will move the lasers, and part solidification, layer solidification will be done. Okay, once the layer is been solidified, the table will move, and it will allow, this movement will allow the next liquid resin to come over the previous deposited solidified layer there, and again this process is, this laser movement is repeated as per the layer profile, and in this way we are able to get a entire 3D part. Now, this has some advantages, some disadvantages. Like we get the high accuracy, very good surface finish. We get very high resolution of small details there, but it has very limited mechanical and thermal strength. Support structure is required. Obviously, liquid may not be able to hold the overhanging portion, so that need to be supported there. Okay, and when we are preparing a part CAD file, simultaneously we need to prepare a support structure file for that part there. Support structures are prepared using the same material, but the process configuration or the structural configuration will be different as compared to the actual part, so that we are easily able to detach the support from the actual model there. But this presence of support will deteriorate the surface quality there, and we may not get the smooth finishing there. This is the stereolithography. Now, as I told you, microstereolithography also work in the same principle, and we have other alternative of stereolithography at the micro level. In the macro level, we call it as digital light processing, or at the macro level, we call it as a projection micro stereolithography machines there. So in a stereolithography, we are actually doing the vector scanning there. That means the point by point scanning. Whereas in the projection micro stereolithography, we are projecting the entire layer profile simultaneously on a layer. Okay. So this increases the build speed. Then we have the some micrometric micro SLM machines, or which we call conventionally called as 2-photon wet photopolymerization. This is very good process for making a micro level components there. Because what we do here in this case, we use a photo initiator. Photo initiator is required to start the polymerization reaction. For to initiate the polymerization reaction, the energy source need to be concentrated at the required point there. So laser is nothing but a photons. So at the position where this laser is striking the surface, the energy is maximum at the center, and outward it will decrease in the radial direction. It will keep on decreasing, and that is actually following a Gaussian distribution. The intensity is following a Gaussian distribution. So to initiate the photopolymerization reaction, two photons are projected at a this, what we call it as photopolymer, where this reaction need to be done, and because of that we get a very good high resolution in this case, very good resolution, and we are able to achieve a feature size of very small size. Okay. This is a two photon wet photopolymerization. Now the question for the micro applications, we need to improve the resolution of this process. So resolution means that I need to improve XYZ resolution of this. So Z we define for the build direction. So we say that the layer thickness direction, or that we call as the thickness of the layer need to be improved. And XY we define at the layer profile direction. So we need to improve the lateral resolution. So commonly we think that if I provide a resin of less thickness, I am able to improve the thickness of the layer. But actually it is not true, because when I am using a laser to solidify this resin, this laser has the more penetration depth than the liquid resin thickness there. Okay, so it may cure the layer below it. Okay, so instead of providing a resin of a less thickness, the better approach is to control the photopolymerization so as to improve the resolution in this direction. Okay, so that can be done using two approaches. First is that I can irradiate the portion using a laser which is having the power close to the irradiation threshold. That means to start a photopolymerization reaction, I need to supply a minimum amount of energy which is required to cross the threshold, so that the photopolymerization will, which is actually a chain reaction, will take place. Okay. So I can use, that means I can irradiate that particular location for a small duration of time, which is enough to achieve the irradiation threshold. So this is very simple and effective way to produce thinner layers, but it has two major drawbacks. First one is a poor mechanical properties, and second one is the precise control of layer thickness is extremely challenging. Because I am controlling the irradiation time, and slight variation of this time may result in that I am providing the more energy. Or since I am solidifying the inner portion by scanning layer, so it may be possible that two scans may cross each other. That depends on the type of scan methodology I am using, but two scans may cross or overlap each other there. Okay. And as a result, at a crossing point, more energy input may take place. Okay. So this is not a suitable approach to reduce the time duration of irradiation. It's not a suitable approach to get the micro level accuracy, micro thickness along the Z direction there. Okay. The best approach is that we use that type of photopolymers which is having a small current thickness there. That means thickness up to the laser is going to solidify that particular resin. Okay. So Using strongly absorbing radiation wavelength photosensitive media result in small thickness as light is confined to the surface. Okay, so I can use a type of polymers, photo liquid polymers, which have the small current thickness. Okay, that is the way to get the micro resolution along the build direction. Okay. Now for the improvement of the lateral resolution, that means the profile I am generating, the size, I need an improvement there. I have to use a laser beam diameter of small size there, and as well as the accuracy of my scanning system, which actually consists of galvanometer, to be high, so that I am able to generate a small feature within the defined tolerance limit. So I can improve the resolution of the stereolithography process for micro scale part fabrication application. But despite this, there are issues associated with stereolithography, and as a researcher or as a user, we must be aware, because it is our job to look for the solutions for these issues and then inform industries that these are the solutions. You can then use this process for actual applications there. Yeah. Now these issues are common in macro as well as in the micro scale. Obviously, when you understand clearly that the layer-wise nature of the process results in stair steps, shrinkage will definitely take place. This shrinkage may result in the curling and warpage of the part. There may be accumulation of the residual stresses, which may also be responsible for the crack generation. There may be unfilled region that laser may not able to solidify the entire resin there. Okay, we may get the part distortion there, like in this overhanging structures. Okay, or in this case, we may not. We are getting the distorted profiles of this oval and the circular shape there. Okay, warpage and shrinkage, curling effects are there. That may be some issues associated with this process there. As for the material, we understand we have to use the thermoset polymers, which solidified on thermoset are polymers which solidify on exposure of heat. So we have to use such type of polymers only. But remember, for the microstereolithography, we have to prefer those polymers which have the small cutting depth there. This has many advantages. Process has advantages like we get a smooth finish equivalent to the injection molded part. We can get a fine feature with high details. We get a high stiffness. The part will be brittle. Because of thermoset, polymers we are using not suitable for outdoor use, susceptible to create such type of problems maybe. There are many commercially available printers based on the microstereolithography are there. I have presented only two of them. One is this UniRapid 3. This is an industrial printer from a UniRapid company from Japan there. And there is another printer that is Photonic Professional GT. This is from Germany. Okay. This particular printer is based on the two photon polymerization process there. Okay. And there are other companies whose commercial printers are also available in market there. Okay. So this is about the micro stereolithography. Here are some of the parts built using these commercially available printers there, like micro connector assembly. You can get, as you can see, entire assembled consolidated part as a single unit. Yeah. You can get the micro channels with built-in micro turbines using these processes. Okay. Then the next is technology which I want to discuss with you is the powder bed fusion for micro fabrication. Now, as I already informed you that at the macro level, this is very good technology, that it has very commercial applications there. But at the micro level, it has limitations. Okay, we are not able to produce actual micro size part. We are getting parts at the level of 500 microns there, and most of these machines, I have not come across any data which shows that they are commercially available. All of the information is at the research level. Some paper publications or the lab documents are there. Commercially, I have not come across. It may be commercially, I have not come across um, any manufacturer which is able to produce micro fabrication machine based on this powder bed fusion process. Okay, so this is the another end of the additive manufacturing coin. We try to understand why it is like that. Because in this case, the feedstock is the major, the shape of the feedstock is a major disadvantage. You require a smaller powder particles, but you cannot reduce a particle size beyond some limits there. If you go for a smaller powder particles, automatically agglomeration of this smaller particle will take place and you will get a large particle. Okay, so this is a problem there. Then smaller size particles are more susceptible to contamination like corrosion or humidity there. Finer particle particles, you may not get a higher bed density because you see if you are joining spherical balls together, there will be a gap present and we may not get the completely filled bed there. Okay, so these are some challenges this case there. Okay, now if I look into this thing, powder bed fusion process is consolidation mechanism is there. To try to understand what is the powder bed fusion process is there, I believe it is known to everyone that in this case we have to spread a layer of powder and then an energy source which may be a laser or an electron beam move over this layer, and wherever this energy is striking at the location, the sintering will take place, which is actually predominantly partial melting or full melting, and we get the consolidated unit there. Okay. So fusion mechanism is basically classified into three categories: solid phase sintering, chemically induced binding, liquid phase sintering, and full melting. Okay. In a solid phase sintering, the temperature is a temperature and time dependent process. Okay. It is a temperature and time dependent process there. So powder particles will come together and they fuse themselves without applying any external force. Okay. So we increase the temperature or time, this fusion will be better. Otherwise, the neck will form. Some porosity will be there. Okay. This is not a predominant mechanism in a powder bed fusion process there, but as there are a heat affected zone, in that zone, this may be one of the mechanism which is taking place, affecting the part dimensional accuracy and the surface finish. Then the chemically induced sintering means on thermal activation, some chemical reaction between the powder particles result in byproduct. That byproduct is responsible for the binding or the agglomeration of the powder particle. Then the liquid phase sintering or partial melting there. This has major application in powder bed fusion. It is basically classified as distinct binder and structural material or indistinct binder and structural material. In distinct binder and structural material, the binder and the structural material are separate phase. Structural material means those material which will constitute the entire object there, where the binders are only used to consolidate those structural material together. So we can have these binders as a separate particles, that means mixed properly with structural materials and binders are mixed properly, or we may have a composite. We may have a powder particle which is nothing but a composite, contain the structure as well as the binder material. On providing heat, the binder will melt, or as a coated particle. That means the structural powder particle is coated with some low melting point polymer. Okay. In distinct binder and structural material, we have no distinction between the structural binder or structural material here. And when we provide the heat, the smaller size particles or lower melting point particle, smaller size particles will melt, and the melt flow will take place, and this collaborate together all the powder particles. That is solidified particle. In both the cases, there is chance of porosity there. We may not get the 100% dense part there. And another, which is nowadays most popular, and SLM, that is structural laser melting machines, are based on this principle, is the full melting. That means we get the complete melting of the powder to take place using high energy, high focus energy sources there. Okay, so this has the less chance of porosity, and we are able to get a part of density 99.97%. Then this process has a number of parameters involved there. Just like other additive manufacturing processes, are also parameters involved there, and we need to understand the influence of these parameters on the part structural strength. And most of the parameters are strongly independent and mutually interacting. I am showing this for the case of powder bed fusion process, but that is also true for all other additive manufacturing. Even for the steel lithography, before application, we need to go for understanding what is the influence of parameters and their interaction effect on a structural property of the part. So I believe if someone has any question, they may ask me here. So my basic aim for this presentation is to give information regarding the understanding related with the additive manufacturing process with micro scale fabrication here. And I try to use two different technologies, stereolithography and powder bed fusion process here, to highlight the challenges here. I started with the pre-processing step that is common for understanding this domain. And if I have some question, you may ask me.
So if you have any queries about this lecture, then you can ask. The session is open for question and answer session.
Sir,
Yes, sir.
actually, when we use the additive manufacturing process, the microstructure and the mechanical property of the whole product is the same,
No, sir.
or it will be different.
No, sir. It is not same, sir. It will vary. As I show you in this window, that there are many process parameters which are affecting. Okay. Now, one of that is the material related process parameter. I am just giving you one example. Okay. Other are also responsible for anisotropic properties in the structure there, but one you can consider the material layer. Like I am using a powder. Okay. Now it is not possible that every layer I am depositing, every layer of powder I am depositing, I am getting the same powder density and the similar powder configuration I am using. Okay. And during the process, the scattering is spatters are also generated here. those patterns are also distributed here. Okay, and this may affect the powder distribution, and as a result, when I am doing the consolidation of these powder particles, I may not get the uniform density. This is one aspect which is responsible for void formation of the crack in the powder particle. Okay. Another is the type of scan pattern I am using. Okay. I have not presented those things in this lecture here. Okay. But that scan, the manner I am scanning the surface there, that means the manner I am inputting the energy in the medium there, that is also affecting there. There may be some region where the excess of energy will be inputted, where there may be some region where the less energy may be inputted there. Okay, so that is also affecting the properties there. And then the entire powder layer is not at a constant temperature. The region near to the laser or the electron beam source is at the higher temperature compared to the rest of the powder bed there. And there is continuous melting and remelting of the already solidified layer is taking place there. Okay. That is also inducing defects in the part there. And so we may not get the homogeneous microstructure, as well as we may not get the homogeneous properties there. So anisotropic will be there in this part.
Okay, thank you, sir.
Thank you for asking.
Dr. Sood, like nowadays, what it is being observed that for a regular kind of object, when you are 3D printing, in order to make it in a mass scale production, if we can put that product in the z-axis, n number of items can be prepared. Right. The xy is the table movement, but along the z-axis, if you are making similar kind of product which is regular, let's say you are making a spar gear of certain dimensions. So if you can make say 3, 4, 5 items along the z-axis, I think that's how they are making this mass production of
Important point, sir. That's why I have earlier discussed the workspace optimization. That's the build chamber which I am having. I can.
Yes, sir.
So I discussed that thing that is known as the workspace optimization.
Right, sir.
Okay. So the build chamber I am having, I have to optimally use that space to fabricate multiple parts there.
Right.
It's not like that in additive manufacturing. I can build similar type of part. Like you have given an example of spur.
Yes, sir. Dissimilar parts can
be different geometries. Like I can same build setup. I can make a spur gear. I can build a glass. I can build a horse. I can build a Buddha statue.
Right.
Okay.
Yes, that is there.
The only thing is the material will remain same.
Right.
But and then we have the direct energy deposition process where we have the capability even to change the material deposition at various locations.
Right.
You can have the heterogeneous material distributions.
Yeah, the layers can be varied. Depending upon the complexity of the object, you can vary the layers also.
Yes, that we can do there. But still these process, they have to be performed in a limited volume. So when we talk about the limited volume, so that also restricts the Z height.
Z-axis.
Okay. So I cannot vertically extend infinitely.
Yes. The maximum height that
I can achieve there.
Yes.
So this
goes to the 000 position.
Yes. So this is another research area where that is known as the bin optimization problem.
Right.
Where scientists use various optimization procedure to optimize the workspace. How to properly use the workspace there. Like you rightly mentioned, if we do that thing and we are able to get a part in a multiple number, that is there. And best part is that simultaneously when the operation will finish, we will get all the parts simultaneously. We can take out all the parts there. But then there is some disadvantage also there.
The post-processing.
Like one disadvantage is that suppose you are building a spur gears, only spur gears.
Right.
So there may be a spur gear at the bottom portion which are built earlier.
Right.
Above that we are building spur gears. So
Right.
those spare gases are been built earlier that will remain in this heated environment for a longer period of time.
Right.
So grain refinement may take place, or they may induce some defects.
Right. Exactly. That may happen.
And
That you have to compromise. That you have to compromise.
that if you, depending on your application, if you are ready to compromise, you compromise.
No, but the thing is like if you are going for metal printing, then also it is possible. Metal printing.
Even for the case of the polymers, there.
Right.
Like what we do in the built environment optimization, we separate these various parts using which we are building vertically using support material.
Support structures. Yeah, that's an additional
Support
work you have to
structure.
do during the post processing.
But if say if the cost is compensated by the batch size,
Right.
then we will prefer that thing. But using this support structure is also adding roughness in the part.
Right.
So later on I have to remove it.
Exactly. Additional operations are included.
Additional operations are given. So you can do a lot of things, but you have to decide judicially that what is the best option.
Right.
So
Sir,
still
another
you can
thing
say
is
that it is not for the mass production. Batch production is good.
Right, sir. Sir, another thing. Have you any idea like this PLA? PLA can be used for making implants used on humans. Is it compatible? Have you any idea? PLA.
PLA, I never worked on PLA. So if it has a biodegradable properties,
yeah,
that can be used there.
Like we are having some orders from dental college. So what they're doing is like they are making crown of the teeth. So they want to have a 3D printed crown. Now we said like I have gone through some of the research works and I found that PLA is compatible and it is non-reactive on human. So I just want to verify with you whether it is really true. We can go for PLA and make those implants, and which will be directly used on humans as a teeth crown.
Sir, that I told you that I need to check on the PLA biodegradable property and their compatibility with for the humans there.
Right.
I have not gone through that thing. But most of the work in polymers in ABS.
Right. Because of the strength part and the durability part, ABS is good.
But if it is there that you can do it, you can use these reverse these scanning methods to get the cavity profile, and then you can
yes
do this thing. And there are a lot of applications in making these teeth implants in using additive manufacturing.
Yes.
You get a lot of data related with that, and through that you can check this PLA.
But the thing is, when they are giving me the data, that the actual data of a person, which is unique.
Yes.
Unique data because the tooth are different for different human. The profile of the tooth is different from different human.
This is the advantage, sir, of this process. You can go for a customized.
Exactly, customized implants. Implants.
Yes, sir.
The thing is that they will be bringing the image or the impression of the tooth. They'll be providing us and we'll be making the crown of the tooth.
Yes, sir.
For the implants.
That could be a good project, sir. You can try that thing.
Yes.
Whatever I can help, I will definitely involve myself.
Right, sir. So that's the thing we are doing right now because we have the Idea Lab that you have heard. Like,
yeah, I am informed with that thing. I know.
Right. So we have some of this equipments of 3D printing and this reverse engineering. We have the 3D laser scanner for reverse engineering.
I will definitely visit your institute, sir.
Sure, sir. It will be my pleasure, sir. It will be my pleasure, and it will be my, a great achievement to bring you to my place, sir. Yes. It was nice hearing from you, sir, with this knowledge and the fundamentals of 3D printing that you have explained so elaborately with all the different domains of 3D printing. And yes, I know that you are working in this area for quite some time and you have achieved certain heights in this area. It was really heartening to hear from you after a long time. So I was a student in your class. It was really nice.
It's my honor, sir, to present.
No, sir.
Front of such a learned faculty member.
Actually, this type of faculty development program actually helps us to gain some information, the latest informations on the wide field of this engineering, mechanical
Definitely,
engineering
sir.
is a very diverse field. So people
And this
like you,
online mode has helped us.
yes, sir.
Earlier, there is no time constraint. You can attend
Right, right,
as
right,
and when required there.
right, sir. So it is really an honor and privilege
Thank you very much, sir. It's my
have
honor.
you with us in this wonderful faculty development program. I hope all the faculty members have really enjoyed. And sir, to for your information, in our faculty development program, not only the academics people are joining. Some of the participants are from industry also.
Oh, that's very good, sir.
Okay, so
Industry participation is must, sir, for the success of
exactly,
this.
exactly. So this time we have a lot of industry persons
Mm.
who are working in the vicinity of Haldia.
Mm.
So they have shown the eagerness to join this faculty development program. I hope this lecture of yours will also give an impetus to their knowledge domain, as well as if they want to do some research work in this area, it will also be very helpful. Now, I must thank at this juncture AICTE for providing us this ATAL FDP program, as well as our institute, Haldia Institute of Technology, for providing us all the logistics and all the support from the institute. We are really glad to have the total support from our institute. My co-convener, Professor Dr. Abhishek Mondo Samanto, he has worked day in and day out for arranging this type of faculty development program, along with his team members, Shirup Banerjee, Supriyo, then we have um, Pritam Pine, then we have um, other faculty members in our department, Patnaik. Now, all the participants, I like to thank you for attending this online faculty development program. I hope this lecture on the additive manufacturing for fabrication is really going to help you in, because this is a new area. This 3D printing is a very new area in India right now, and it is an emerging field. Lot of work is being going on abroad. So I hope this will also help the new researchers who are venturing into going for PhD work. This will really help. Okay, so if any further queries, you can contact us. We can give you the support, as well as we can help you contact Professor Anup Sood. He is an expertise in this area. He's working in this 3D printing and additive manufacturing for quite some time. So all in all, I think this was a wonderful event today. So thank you all. Thank you, sir,
Thank you
for
very
your
much. It's my honor,
presentation,
sir.
sir. Thank you, sir.
Thank you. So I'm
So
taking leave, sir, with your permission.
yes, sir. So we are signing out. Thank you all. Good night.
Thank you. Good night, sir.